Hi, this is Mori reporting from Berlin, and this is part 10 of my using Reactors with D3 series. And in this one, I want to show you how to create this animated tree chart right here. So it will animate if I reload the page, like so, and it will also animate when we update the chart. Yeah, that's it. Stay tuned. So in this session, we will be rebuilding this chart here from scratch. And in my app here, I just have some initial data. It is nested. It is like hierarchical. And you can see that this like main node or root node here has some children. It has two children. And then the first child has three children of its own. And it is important that this structure here looks like this, because per default, when we want to work with D3 and create this chart, D3 will look for these like children properties, but you can also use different properties if you like. So I am passing this data to my tree chart component down here, and I also have this button which says update data, and if I click it, it will reset the root node. It will then take this node you can see here, the first child, and set it as the root node, as you can see here. So now I cleaned up my tree chart component. It's the same boilerplate component which I've been using for a while now. You should be familiar with it. If not, just check out some of my older videos. I'm just rendering an SVG here, accessing it in my use effect hook, and then applying some like D3 magic here. And I'm also using this use resize observer hook, which I created in a former video to get the current dimensions of my SVG, which I have here, to render my D3 charts. So what we need to do first is we have to import something from D3 called hierarchy. And this function will transform the data we have, and it will enable us to extract the nodes and the links in our data. I will just demonstrate by going over here and saying const root equals hierarchy, and here I will just pass the data we have. And then I will just log the data we have, and also I will log the root object we have here just to compare them. So yeah, here you can see the data we have. This is our initial data. It has a name property and two children. And this is the root object we logged out. It looks a bit different. It has this data property, which is actually the data we logged out earlier. And then it also has like a depth property telling that this node, which I just logged out, is the root node. It has a depth of 0, and children of this node will have a higher depth. And we can see these children by looking at this children property, and you can now see here it has two nodes, and the first node, or the first child, also has its own data property and also its own depth. Now you can see that the depth increased by 1 for the first child. And also, if you look at the prototype of this object, you can see like functions which will help us to determine all the descendants or all the nodes of that root object. Yeah, we will use descendants to get all the nodes, and we will use links to get all the links between the nodes we have. So let me demonstrate the descendants and the links by logging them out, like so. And this we don't need. So let's look at the descendants first. The descendants, you can see here, is a flat array with 6 nodes, including also the root node or the root object. And you can see it has the depth of 0, and then come the 2 children of that node, and then the 3 children of the first node. And this array, this flat array, we will be using for rendering all the dots or the nodes on our tree chart. So now let's look at the links. The links array is also a flat array of 5 objects, and this represents all of the direct connections in our data array. And you can see here, for example, the first one, or each object in this array has a source and a target property, which points to the different nodes we have. For example, this first link describes the link between the root node we have and one of its children on the first level. And these links we're going to use for rendering the links or the lines between the nodes. So we could render all of the nodes and links manually if we wanted, depending on the nodes we have and their depth. But it is actually a lot of work, and the D3 makes it easy by using like some of the utilities it provides. And yeah, here's some of the utility D3 provides to transform the hierarchical data we have now into like a visual representation. And one of them is called cluster, and another one is called tree. It is very similar to cluster actually. And this is what we're going to use in this session. So tree will take the data we have and like enrich it by adding also like X and Y coordinates to that hierarchical data we can then use for rendering the nodes and links. There's also like tree map, which works a bit differently, and it looks like this. Let me demonstrate how this tree function will help us to like render our nodes and links in our SVG. I will just go here and say const tree layout equals tree. And here I just have to define one thing, the size of that tree, and with an array of like width and a height. And the width and the height we have in our dimensions object from our useResize observer. And here I'm just going to pass dimensions width and dimensions height. And then I have to call the tree layout, which is a function, with the root object, which I want to enrich with X and Y coordinates for each node. Yeah, let's see how this looks like. So now let's see how the descendants and the links look like after we enrich our data with the tree layout function. And if I look at the descendants and at the root node, I will now see that it has an X and a Y coordinate, which was not there before. And these are calculated based on the width and the height of the tree layout we want to generate. So now let's start by rendering our nodes. And for that, we're just going to use the general update pattern we've been using so far for D3. We're going to say, hey, D3, select all the existing elements in my SVG with the class name node and synchronize them with the data I'm giving you here. And the data is now going to be the descendants array we just logged out earlier. And then I'm going to say join. So create a new circle element for every new piece of data, and also attach the attribute class node to every circle so that they can update later. And yeah, this will generate the 6 circles we need in our tree chart. So now let's make these nodes visible by attaching some attributes like r, the radius, let's say 4. And then we want to say it has a like black filling, like so. And then we want to define the X and the Y coordinate of each circle. And for that we have to say attr cx. And here we'll pass in a callback function which receives the current node in our descendants array as an argument. And here we can just pass the X property to define the coordinates of that circle, and we can do the same for the Y coordinate like so. And if I save this, you'll see we have now 6 nodes. And the important thing to note is that this tree layout renders a vertical tree per default from top to bottom. And this node you can see here is actually our root node. Then you can see the 2 children of that node, and then you can see the 3 children of that node. So we will transform this vertical tree into like a horizontal tree later on. Yeah. So for the links in my chart, I'm going to use another utility from D3 called link vertical. And it's called vertical because the links are going to start here from the bottom of a node and attach to the top of another node. And yeah, then I'm going to go down here and say const link generator equals link vertical. And here you can set a set of things, but let me explain how this works. The link generator will then later on receive one of the link objects we have logged out here earlier. And it will want to know, okay, what is my source node and what is my target node? And that is why you can set the source accessor and say, okay, when you receive this link object, use the source property. And for the target node, use the target property. I'm going to pass in the link as an argument and say link.target, like so. And then this link vertical will want to know, okay, I now have the source and the target node which I want to connect. And to render the link, I need to know, okay, what is like the x and y coordinate of the start node and what is the x and y coordinate of the target node. And for that I have to define like the x accessor, and this will receive the node which we are accessing in this source and target accessor. And here I will say, okay, when you look at the start or the target node, use the x property of that node. And when I look at the y property, just use the y property of that node. And these two actually, or the source and target accessors I have just defined, like this, it is actually a default, so I don't need to define them. Yeah, because like this link vertical will look for like a source and a target property of a link object anyway. So now that I have the link generator, I can use it to render the links in my SVG, and these links are actually going to be path elements, and the link generator will help us to set the D attributes of these path elements. And like I said also in the former video, the D attribute of a path element like defines its shape, where it starts, where it ends, and how it's curved, and so on. And yeah, the link generator will help us with that. So now let's go forward and use this link generator to render and display our links finally. So same as before, general update pattern. I'm going to say, hey, D3, select all the existing link elements you find in my SVG and synchronize them with the data I'm going to give here. And it's going to be root.links this time instead. And then I want to say, okay, I want to create a new path element for every new piece of data, and I want all of them to have the class link so that they can update later. And this will generate these 5 links for me, but they're not visible. And now to make them visible, I have to say attribute D. So the D attribute, like I said, is going to be handled by our link generator. And yeah, this is where I can say, okay, I'm going to receive the current link object and pass it to my link generator, like so. But this expression I can also just write like this. I can just say link generator. And if I save this, we should see something, yeah, some ugly shapes. But we can fix that by saying attribute fill none, and by defining stroke like so. And if I save this, we will see some beautiful links between our nodes, and this reflects the hierarchy or the structure of our initial data array. So what we're going to do next is we're going to flip this vertical tree chart into a horizontal one. And to do that, we just have to adjust our accessors actually. We just have to flip the x and y values like so. Y and x. And if I save this, it will look like this. Kind of right, not quite. And we also have to actually flip the width and height for the size of our tree. Say height and width. And this will make our chart look like this. And also what we have to flip is we have to not use link vertical, but link horizontal. So yeah, I'm gonna replace that here. And if I save that, you'll see that our chart now looks like this. Yeah, I also just went ahead and positioned the emojis. Yeah, it's nothing special. I'm just using the general update pattern again, rendering a text element. For the content of that text element, I'm accessing the node and then the data property where our data is saved, and accessing then the name property, centering it, and yeah, positioning it. So now for the more juicy part of this tutorial, let's animate these links. And to do that, we have to work with something called stroke dash array and stroke dash offset. And yeah, let me explain what those are. So stroke dash array and stroke dash offset are both attributes you can set on a path element to define how the stroke is basically dashed. And I will just start with the stroke dash array by saying enter stroke dash array. And then here I'll just work with hard-coded values for now. I just have to pass in two numbers. I will say 100 and 50, for example. If I save this, you will see that the path will render its stroke for like 50, or I'm sorry, 100 units, and then stop for 50 units, and then render again for 100 units, and so on. And what stroke offset does, I'll just demonstrate enter stroke dash offset. It will just yeah, add an offset or shift this like pattern of 150 by a fixed value. I'll just say like 100, and if I save this, you will now notice, or you might notice, that the path now starts with doing nothing for 50 pixels and then rendering its path for 100 pixels. So the trick behind this animation is to set all three of these values to the very length of the path we're currently working with. And let's for now estimate that the length is like 225 units long, like so. And if I save this, we will first see nothing, and that is normal because we're telling the path to render a visible line for its entire length, 225 units, and then we're saying, like, outside of the viewport to render an invisible line for 225 units. And then comes the dash offset, and we're like shifting this invisible line back to the very beginning, and that is why you're currently seeing nothing here in my browser, or no lines in my browser. And the goal then now is to like animate this dash offset 225 back to 0, so that the invisible line moves out and the visible line moves back in. And that is the whole trick behind the animation. And if I were to, for example, now set the dash offset to 0, we would then see the line again. And yeah, another goal we have to, or another thing we have to determine is the actual length of the path element itself, because we're currently just estimating. Yeah, just to demonstrate that this idea works and that this is actually our goal, I set the stroke dash offset again to this hard-coded 225 value, and then add this transition to transition this same attribute down to 0. And yeah, this results in the animation of these links, as you can see here. And now the goal is to actually determine the yeah, the actual length of the path. So now I want to determine the actual length of each path element we have here, because now with a wider browser here, this hard-coded 225 value doesn't work. And yeah, to determine the actual length, we have to access the current path element we're currently working with. That is because every path DOM element has a method called getTotalLength, which returns the actual length of a path element, which we need to use here. And to access the path element itself, we have to pass in like a callback function here with the actual function keyword. And that is important because we have to use this keyword, which always refers to the current DOM element, or in this case, the path element we're working with. And that is not available in arrow functions. And yeah, that is why we're using the function keyword. And yeah, now for the length, it is going to be const length equals this get total length. It is also actually being auto-completed. Wow. And now we have to return a string like before, but not with the like hard-coded values. We have to return it with the like actual length of the path. And we have to make it look like this. Like one length for the visible part and one length for the invisible part. And for the stroke dash offset I have here, I basically have to do the same thing. But I don't return a string, but I return the length here instead as just the value. And if I save this, oops, no, here. And if I save this, this should now work like no matter how wide our browser is. Looking good. And one more thing we should do is we should animate these links like one after another in a staggered way. We should first animate the links from the root to this level here, and then to this level. And to do that, we can just delay the animations depending on the depth of the current node. So to have this staggered animation, I'm going to go to my transition and set a duration, like 500 milliseconds. And then I'm going to delay this transition depending on the current link object we are currently working with here. And this is why I'm going to define a callback function which receives the current link object. And then I'm going to look at the source node like of that link and look at the depth value and multiply it by 500. So yeah, this will like make sure that there's no delay for the very first link because the source depth is 0, and then for this level there will be a delay of 500 milliseconds because the source depth here from here to here is 1. And if I save that, you can now see we have this staggered animation going on. So the same transition logic I just now also applied to the nodes, the dots here, and also the emojis by setting like the initial opacity to 0 and then setting up a transition where I delay the transition depending on the depth of the current node we are receiving from this descendants array. And yeah, same here for the labels. And it looks like this. Oh yeah, and it should also work when I update the data. Yeah, looking good. Yeah, so one little thing I want to address before I wrap up this video. I didn't address it because I thought it would blow up the video a little bit. It's about the responsive behavior. So it is still responsive, as you can see here. But the thing is that the transitions will start over when the browser window, browser resizes. And that is because this code is triggered every time the data or the dimensions change. And my goal was that the transitions always happen when the data gets updated, as you can see here now. But I didn't want that the transitions happen when the like dimensions change. And that is something I didn't address here in this code, but I did address it and fix it in the code I have pushed to the to my GitHub repo, where you can find all the code I'm working here for this series. And yeah, please refer to that one if you want to see the correct behavior. And yeah, that's it for this video. I hope you liked it. I hope you enjoyed it. It was really fun working on this video. So yeah, hope to see you next time.